Okay, we'd like to kind of show you the calculus of a motion graph. If you watched the last video on calculus review, hopefully this will make sense. Let's say we have a velocity, a displacement time graph. So we have displacement here and we have time here. And we have acceleration. We have a car that's accelerating on this. And if you remember, acceleration is a curve. So it looks something like this. And it's a curve, and that should make sense because a curve is a continuous changing of straight vertical lines, and our straight vertical lines would have a bigger and bigger and bigger and bigger slope. And so it makes it into a nice smooth curve. And it should also make sense that it's a curve because we actually know what the equation for this curve is, because we have an equation, one of our three motion equations for displacement when we have constant acceleration. And that equation is d equals 1/2 at squared plus vit. And so this makes sense, I think. This is a quadratic. See, we have displacement is a t squared plus a t. We have the t is our x values here. And so instead of using x and y, we're going to actually be using our t and our d in our problems here. And so the question then that could get asked is, how fast are we going, like right here? Well, that's kind of difficult on this graph. If I was on a velocity time graph, it'd be really easy. I could just go over and read what it says. But on a displacement time graph, I'm not sure. I know that it's the slope of the line that goes through that point that's tangent to this curve. So if I knew the equation for that line or the slope of that line, I could put in a time at that into that equation, and I would be able to, figure out what the slope of that line is. If I had that equation, I could put in time like here and figure out what the slope of this steeper line would be at this point. So what we need to do is we need to apply basically the same calculus kind of that we did last time. I'm going to say that this point here that I want to figure out what the velocity is at that point. We'll say that that's at time, and we'll just call it t to make it easy. We could do t naught, but we'll just call it at time t. And what I need to do is I need 2 points for a slope. So we're going to just come down here a little bit further on the curve, and we're going to take another point. And we'll say that this is at point t plus, a little bit more t, the difference between these two. And in our calculus, we called that h last time for Herman, but this time we'll call it delta t. So t plus delta t. And so we're trying to find the slope between these 2 points, slope of the line between these 2 points. And of course, it's not the best. It's the secant of a curve. I want actually the slope of the line that's right at that point. But we can get to that. We can approximate it. We can find, what will happen to the slope? What will be the limit of this slope as my delta t? If I bring this point closer and closer and closer to this point and make my delta t smaller and smaller and smaller until it gets to 0, when it gets to 0, there will be a limit to what this slope is, and then I'll know. So I can find the derivative, or I can do some calculus on this particular thing. So, what is the distance at this particular time? So for right now, I'm just going to call it d1 to make it easy. And the distance at this particular time, t plus delta t, is d2. And so if I want to find the slope of this, if you remember, slope is rise over run. It's the change in y over the change in x. And my change in y here is d2 minus d1. And my change in x is t plus delta t minus t, which leaves me with just the difference between these two, which of course is just delta t. And so that's pretty simple so far, but we actually know what the function is. We know what these y values, this is y2 and y1, d2 and d1, they're y2 and y1. These are the functions when we put in time for the function, what do we get? Well, we get this. This is the function for this particular curve right here. So I can put at D2, I could put in t plus delta t in for my time to figure out what the function is at that time. And then at D1, I can figure out what D1 is by putting time t in for that. So that's what we're going to do here. It's going to be kind of, it's going to be kind of ugly. So I'm going to have D2, which would be 1/2 a times t squared. Well, what is t for D2? T is right there, t plus delta t. So it's going to be t plus delta t squared plus vi times, and what's t again? It's t plus delta t. And then I'm going to minus d1. What's d1? Well, d1 is this function at time t. So I'll put time t in for my t, which is going to make it easy because it's exactly what's written there. So I'd have minus 1/2 at squared. And then I'd have a minus, again, vi t. And this is all over delta t. So this would be the slope of the line between these 2 points. So we're working this out here. Okay, so this is going to get a little ugly here. So we're going to have to kind of scroll down here a little bit and kind of start over a little further. Let's use some green. And what I'm going to do here is I'm going to, if I can remember, let's see, maybe we should do this slowly. Let's just take 1/2. Let's redo this. So I have 1/2 a times, I'm going to expand this out here. So I'll have t squared plus 2t delta t plus delta t squared plus, and I'll distribute the vi t plus vi delta t minus 1/2 at squared minus vit all over delta t. Okay, so let's distribute the 1/2 a through here, shall we? So we have 1/2 a t squared plus, okay, 1/2 times 2 is just 1, so I'm going to have a t and t. That's funny. Plus 1/2 a delta t squared plus vi t plus vi delta t minus 1/2 a t squared minus vit all over delta t. Okay, can I make this better? Let's see. We have a 1/2 at squared, and we have a minus 1/2 at squared. See that? That's pretty nice. So I can get rid of that and that. What else do I have? Do I have anything else I can get rid of here? Okay, doesn't quite look like, let's see, there's a there's a VIT right there and a minus VIT right there. So that's going to go away and that's going to go away. That's nice too. Okay, so what do I have? I have AT delta t plus 1/2 a delta t squared plus a VI delta t all over delta t. So that means that I can take a delta t out of every term here and not have a delta t in the bottom. So that's nice. So I'm going to end up here with a t, my delta t will cancel off, plus 1/2 a delta t plus vi, right? If I cancel out my delta t. So that's about as far down, I think, as I can simplify it for right now. And so what were we doing? Oh, yes. Okay, so this is the slope of the line between these 2 points up here. And that's not really what I want. I want, what is the slope of the line right here at this 1 point? So what I can do is I can figure out what is the limit of this slope? I mean, how is this slope going to change? What is the limit of this slope as I take delta t to get smaller and smaller and smaller towards 0? What will it be? Well, the way I can do that is I can just put 0 in for my delta t in this equation. If I put 0 in for delta t, this whole term in the middle will be 0, and then the velocity or the slope of the line at that particular point, which we know is the velocity, that's what we're trying to figure out, the velocity at that point, the velocity, we could call it the final velocity, at that particular point will equal AT plus VI. Look at that. That's amazing. So this is the equation for a straight line, y equals mx plus b, right? That's y equals mx plus b. It's the equation for a straight line at a certain point. So all I need to do is to figure out the velocity at any time along this curve is just to put the time into this equation here. I'll take the time times whatever the acceleration is, if the acceleration was given, and add it on to the initial velocity, and I will have the final velocity. So what we have here is we started with d equals 1/2 at squared plus vit, and we took the derivation of this equation to figure out what the slope of the line is at that point, and it ended up being at plus vi. So these are two of our uniform acceleration equations. The third one being the one that we can get from the conservation of energy, which you've already practiced. But these other two equations is interesting because one of them is the derivative of the other. So we take our distance equation, and the derivative of distance is velocity. So we have this equation here being the derivative of this other one. And we can do kind of a shorthand rule of figuring out how to take a derivative if you remember this from your calculus class. For instance, if I have like 3x squared plus 2x plus 1, and I want to take the derivative of this, the quick way to do it, you don't have to do it this long method. It's really easy. You just take the exponent times the coefficient and subtract 1 off of the exponent. And I do that for each term. So if I take 2 times 3, that's 6x, and I subtract 1 off the exponent, so 2 minus 1 would just be 1. So this 3x squared becomes 6x. Plus, what's the exponent on this x? It's a 1. So 1 times 2, I take the exponent times the coefficient. 1 times 2 is 2. And then I subtract 1 off of the exponent. Well, the exponent here is 1. If you subtract 1 off, it's going to be x to the 0 power, which is 1. So that becomes 2. And you could even do it to this last term, but we just know that the last term you don't write down because this would be x to the 0 power. If it was written, it'd be x to the 0 power because that's 1, right? And so what's 0 times the coefficient? It's 0. So we don't have anything else. So the derivative of 3x squared plus 2x plus 1 is 6x plus 2. What's the derivative of this? Well, you take so this is the first function of x, and then this would be the derivative. And now what's the second derivative of this? Well, take the exponent, 1 times the coefficient, 6, subtract 1 off the exponent, x 0, that'd be nothing. And this is the constant becomes nothing. So here's the function. Your derivative of that function is 6x plus 2, and the derivative of this function is 6. Now this second one here should be easy because what is this? This is f of x, so this is y equals 6x plus 2. And what is that? That's the slope-intercept form, y equals mx plus b. So if you remember that all you're doing when you're taking the derivative is finding a slope. That's all you're doing. So it seems complicated when you have a curve and you're trying to find the slope at a single point. It makes it be a little bit difficult because you're going to end up with an equation like this for a straight line. We start with a quadratic, we end up with, take a derivative of that, we get an equation for a straight line. Well, if you take the derivative then of the straight line equation, remember what we're doing? We're finding the slope. And you knew how to do this when you were in junior high. If I gave you this equation right here and I said, what is the slope? You're just looking whatever is in the m. It's right here. It'd be a. That's your acceleration. So it's interesting that, you're in 7th grade and I say, here's an equation and write down what the slope is. I could have easily been saying, look at this equation. Take its derivative. Take its derivative. What's the derivative of y equals 6x plus 2? You'd write down 6. The slope of this line is 6. And you're actually taking the derivative. It's very easy when it's a straight line because you know that the form, the m right there is actually the slope. So if you look here on our equation, we could do this the long or the short way now. We had an equation at the beginning of the curve, d equals 1/2 at squared plus vit. And we were trying to take the derivative. We were trying to figure out what is the slope of a line tangent to one of the points on this particular curve. If I know the function, I can do this really easy in just 2 steps. If I know this function, I want to figure out what is the slope of the line as tangent to the curve because I know that's going to be velocity. It's going to be velocity. So this is f of x here. And then f prime of x is going to be velocity. I just do the rule. 2 the exponent times the coefficient. 2 times 1/2 a is just a. Subtract 1 from the exponent would be just t to the first power. Plus, what's the exponent on this t? It's 1. So take 1 times vi, you get vi. Subtract 1 off the exponent, you get t to the 0, which is 1. And so there is the derivative of this equation. This equation here is the derivative of that one. And then what if I want the second derivative, the second function? Well, the derivative of displacement is velocity. The derivative of velocity is acceleration. And what is it? How do I take the slope? Well, I take 1, the exponent 1 times a. I get a, and guess what? That's all I get. A is constant. A equals a. A is it's a constant acceleration for these things. So these two uniform acceleration equations, the point I'm trying to make is they are related. One of the equations, the car commercial equation, is the derivative of the other one. And hopefully that makes a little bit of sense on how these uniform equations are related to calculus.